6. Completing the 24-cell, the hidden arithmetic structure of four-dimensional geometry. So far, we have looked at numbers as points, but a collection of points becomes much more interesting when we ask how those points are related. Instead of looking at each point individually, we can look at the structure formed by the entire collection. Which points are close to one another? Which points are connected? And what symmetries preserve the structure? These questions lead us from a simple list of coordinates to something much richer, a geometric object with its own internal organization. In 4 dimensions, this organization can be surprisingly intricate. A particularly important example is the 24-cell. It has 24 vertices, all lying at the same distance from the center. Each vertex is connected to a precise set of neighboring vertices, producing a highly symmetric network. But there is another way to look at the same structure. The vertices can be represented using 4-dimensional integer coordinates, and those coordinates reveal a connection with the lattice known as D4. This is where our investigation begins to shift. We are no longer simply drawing points in 4 dimensions. We are studying the algebraic structure hidden behind those points. The same collection can be viewed geometrically as a polytope, or arithmetically as a lattice. And when these two viewpoints agree, something remarkable happens. Geometry begins to behave like arithmetic. Arithmetic begins to acquire a geometry. In the next step, we will use this connection to investigate how points can be transformed, combined, and organized into distinct families. The goal is not simply to describe the 24-cell. It is to understand why this particular structure appears, and what it is telling us about 4-dimensional space. Seven, the action of symmetry. We have seen that a single point can generate an entire family of points through symmetry. But now we can ask a deeper question. What happens when we combine 2 symmetries? Suppose one transformation moves a point to a new position. Then a second transformation acts on the result. The final position depends on both operations and on their order. This is the beginning of composition. Instead of thinking of a symmetry as something we simply perform, we can think of it as an operation in its own right. We can label these operations, we can combine them, and we can ask what operation is produced by their composition. For example, applying transformation A and then transformation B gives a new transformation, A followed by B. That new transformation is itself one of the symmetries of the structure. This is a remarkable property. The transformations are closed under composition. They form an organized algebraic system. And once we have assigned an index to every transformation, composition can be turned into a table. Choose any 2 transformations. Look up the result of applying one after the other. The table tells us which transformation we obtain. This is the action table. It converts a geometric process into a finite collection of algebraic operations. But there is an even more useful viewpoint. Instead of applying every transformation separately to every point, we can pre-compute the action. For each symmetry, we know where every point goes. The geometry has now become data, and that data can be stored, indexed, and composed. What began as a collection of points in 4-dimensional space has led us to a finite algebra of transformations acting on those points. This gives us a powerful computational framework. We can explore the geometry without repeatedly rediscovering the same transformations. And in the next step, we will use this framework to connect the symmetry action with the arithmetic structure of the lattice itself. 8. Examples. n equals 2 through n equals 7. We have now seen how the shell is constructed. The next question is simple. What does this construction actually look like for different values of n? Let's begin with the smallest non-trivial cases. For n equals 2, the equation becomes w squared plus x squared plus y squared plus z squared equals 2. The solutions are obtained by placing two coordinates at either plus or minus 1, with the remaining two coordinates equal to 0. These points form a highly symmetric configuration. Now, increase the value to n equals 3. Three coordinates can take values of plus or minus 1, while the fourth is 0. Again, the solutions appear in symmetric families. Now consider n equals 4. The possibilities change. A coordinate can now have magnitude 2, while the remaining coordinates vanish. But the same basic rule still applies. We simply ask which combinations of integer coordinates have squared length equal to n. For n equals 5, new combinations become possible. And as n increases, the number of integer points on the shell can change dramatically. This is an important observation. The shells are not all the same size. Some values of n produce only a small number of points. Others produce many more. Yet every point is still governed by the same equation: w squared plus x squared plus y squared plus z squared equals n. Let's continue. For n equals 6, we find another collection of symmetric integer points. And for n equals 7, the pattern continues to grow. At first, these examples may look like a collection of unrelated cases, but they are not. They are all instances of the same construction. Choose n. Find every integer quadruple whose squared coordinates add to n. Those quadruples become the points of the corresponding integer shell. The arithmetic determines the points. The points determine the geometry. And the geometry changes as n changes. This gives us a remarkable way to explore the integers. Instead of representing a number by a single symbol on a number line, we can represent it by an entire geometric configuration in 4 dimensions. The number n determines the radius. Its representations determine the points. And the symmetries of those points reveal additional structure. In the next scene, we will look more closely at one of the most important patterns that has been appearing in these examples: parity. The distinction between even and odd coordinates will turn out to be much more than a bookkeeping detail. It will help organize the shells themselves. (9) The parity pattern. In the examples we have just seen, something subtle has been happening. The coordinates of our points are not arbitrary. There is a pattern hiding in their parity. Remember that an even number has the form 2k, while an odd number has the form 2k plus 1. When we square them, something important happens. The square of an even number is even, and the square of an odd number is odd. So, in the equation, w squared plus x squared plus y squared plus z squared equals n. The parity of the 4 coordinates determines the parity of n. If n is even, the number of odd coordinates must itself be even. If n is odd, the number of odd coordinates must be odd. This simple observation has a powerful consequence. The solutions naturally separate into parity classes. For an odd value of n, we can have 1 odd coordinate, or 3 odd coordinates. For an even value of n, we can have 0, 2, or 4 odd coordinates. The arithmetic of parity is therefore reflected directly in the geometry of the shell. Look again at our examples. For n equals 2, the solutions have 2 odd coordinates. For n equals 3, they have 3. For n equals 4, we encounter solutions with all coordinates even. And for n equals 5, the familiar pattern of 2 non-zero coordinates reappears with a different combination of odd and even values. The exact coordinates change as n changes, but the parity rule remains. This gives us a way to classify the points without examining every coordinate individually. We can look only at whether each coordinate is even or odd. That produces parity signatures such as E, 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 O, O, E, E, or O, 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 E. The actual values may change, but the parity pattern tells us something fundamental about the shell. And now we can see that parity is not merely a property of individual numbers. It organizes the entire collection of four-dimensional points. This will become especially important when we move beyond the integer shell, because there is another possibility. Instead of coordinates that are all integers, we can consider coordinates that are all half-integers. The distinction between these two kinds of points will lead us directly to a much richer four-dimensional structure. And that structure will bring us to one of the central objects of this chapter, the 24 cell. The 24 cell and the general construction. We have reached the point where the pieces come together. We began with a simple question. How can a number be represented as the sum of four squares? N equals w squared plus x squared plus y squared plus z squared. We discovered that every solution can be viewed as a point in four-dimensional space. For a fixed value of n, all of these points lie on a four-dimensional sphere. But the integer points are only part of the story. Our parity analysis revealed a second possibility. The coordinates can also be half-integers, so we have two families, integer coordinates and coordinates that are all half-integers. Now consider the smallest non-trivial shell. The integer family gives the points, plus or minus, 1, 0, 0, 0, and their coordinate permutations. These give 8 points. The half-integer family contributes the 16 points, whose coordinates are all plus or minus 1 over 2. Together, the two families contain 8 plus 16 equals 24 points. And these 24 points form one of the most remarkable regular structures in four-dimensional geometry, the 24 cell. The arithmetic has become geometry. But there is something even more interesting. The same construction is not limited to this one shell. For any positive integer, n, we can begin with the four-square equation, w squared plus x squared plus y squared plus z squared equals n. We can enumerate its integer solutions, we can examine their parity, and we can construct the corresponding geometric shell. The number n determines the radius, the four-square representations determine the points, and the symmetries organize those points into geometric structures. This gives us an algorithmic way to move from an integer to a four-dimensional configuration. Start with EO, find its representations as four squares, classify the resulting coordinates, generate the corresponding point set. Then, study the geometry and symmetry of that set. What began as a question in elementary number theory has opened a door into four-dimensional geometry. Numbers can become points. Points can become structures. And structures can reveal new arithmetic. This is the central idea of our journey. In the chapters that follow, we will go further. We will explore the lattices behind these point sets, the transformations that preserve them, and the algebraic structures that connect the geometry back to arithmetic. The four-square equation was only the beginning. The geometry was there all along.